A 2,000-year-old dome stands intact while a modern overpass crumbles after 50. This is the mystery of ancient concrete, a material that could heal its own wounds. By the end of this, you will understand a lost science that could redefine how we build our world. How did Roman harbors thrive in salt water that destroys our own? And what crucial ingredient did medieval monks understand that we have forgotten? What does it say about us that our strongest materials are often the most fragile? This discovery was less like finding a new tool and more like unlocking a secret language spoken by the earth. Pozzolana, that fine volcanic ash, was the key to the untrained eye. It was just gray dust, but to a Roman builder it was the heart of a miracle. When they combined it with slaked lime, extraordinary happened. Ordinary mortar simply dries out, binding materials together until weather and time wear it down. But the Pozzolana mixture began a chemical conversation that never truly ends. The lime provides a highly alkaline environment, and the fine, glassy particles of volcanic ash dissolve in that environment, beginning a process called a Pozzolanic reaction. This creates new, incredibly stable crystals that weave themselves through the mixture, filling every microscopic pore and void. Think of it not as glue that hardens and becomes brittle, but as a living network that grows denser and more interconnected with age, especially in the presence of water. That last part is crucial. While water is the enemy of modern concrete, seeping into rust steel reinforcements and cause cracks, it was the catalyst for Roman concrete. The architect Vitruvius understood this intuitively. He wrote that structures made with this material grow stronger not just on land, but remarkably beneath the waves. This is why Roman harbors, like the one at Caesarea Maritima, could defy the relentless saltwater for 2 millennia, while our own seawalls require constant, costly repair. The material didn't just resist the sea, it used it, drawing in moisture to fuel its ongoing internal growth. This sets up a profound question. If the Romans had this self-healing, eternal stone, why did the recipe vanish for over 1,000 years, leaving medieval builders to puzzle over the crumbling ruins of a world they could no longer recreate? The secret lies in a conversation between stone and water, a chemical dialogue we once understood as a form of alchemy. This is the lime-clastic reaction, the timeless bond that gives ancient concrete its living quality. To grasp it, we need to think differently about what makes a material strong. Modern Portland cement, the backbone of our world, gains its strength through a rigid, crystalline structure. It sets quickly and firmly like a single, massive block of ice. It is hard, but it is also brittle. A crack in that ice can spread because the material has no way to stop it. The ancient recipe worked on an entirely different principle. When Roman builders mixed their slaked lime with pozzolana, they were not just making glue. They were initiating a slow, persistent reaction that creates something far more sophisticated, a gel-like substance called calcium-silicate-hydrate. This material, often called CSH, is the hero of our story. Unlike the rigid crystals of modern cement, this gel is more flexible, woven through with countless microscopic fibers. It is less like a block of ice and more like a dense, mineralized sponge or even a living coral reef, constantly interacting with its environment. This structure is the key to its magic trick, self-healing. Imagine a tiny crack no wider than a hair forming in a 2,000-year-old seawall. In modern concrete, that crack is an invitation for disaster. Water seeps in, freezes, expands, and widens the breach, or it reaches the steel reinforcements inside and begins to rust them, causing even greater damage from within. But in the Roman mix, that same droplet of water becomes a healing agent. As it travels into the crack, it dissolves tiny, unreacted particles of lime that are still present throughout the concrete, even after centuries. This creates a saturated solution, a kind of mineral-rich fluid. This fluid then reacts with silica from the pozzolana, or even with carbon dioxide from the air, and it begins to precipitate. It deposits new, solid crystals of calcium carbonate or more CSH gel directly inside the fissure. Slowly, patiently, the crack fills itself in. It is the material's own immune system, a built-in repair kit that activates precisely when and where it is needed. This is why those ancient structures could stand in the pounding surf, because every small assault from the sea triggered not decay, but a microscopic act of regeneration. The concrete was not fighting the elements, it was using them. This inherent ability to self-repair stands in stark contrast to the brittle, static nature of many modern mixes. Our concrete is designed to be perfect on the day it is poured, but it is a perfection that only degrades. Theirs was designed to be imperfect, to contain within it the seeds of its own perpetual renewal. So if this knowledge was so powerful, why did it fade into obscurity, leaving medieval architects to stare at impossible vaults they could no longer build? The fall of Rome did not shatter the knowledge of concrete, it simply scattered it. Across the fragmented landscapes of medieval Europe, the grand imperial recipe book was torn into pages, and those pages were carried into monasteries, guild halls, and castle yards. Here, the universal science of Rome became a collection of local dialects spoken in stone and mortar. Medieval builders, particularly within monastic communities who preserved classical texts, faced a fundamental problem. The miraculous volcanic ash, Pozzolana, was a material of specific geology. It was not found in the forests of France or the river valleys of England. Without it, the living, self-healing concrete seemed an impossible dream from a lost age. Yet, when we look at the stone skeletons of medieval cathedrals or the deep foundations of Norman keeps, we see that something of that dream survived. How? The answer lies in a profound shift from universal recipe to localized adaptation. These builders became alchemists of the commonplace. Lacking volcanic glass, they learned to create its reactive properties from the materials at hand. They discovered that by crushing old bricks, pottery shards, or even certain types of burned clay and mixing them into their lime mortar, they could mimic the Pozzolanic reaction. These were artificial pozzolans. The chemistry was similar if less potent. The high-temperature firing of the clay or brick created amorphous, glassy silica, which could then dissolve in the alkaline lime slurry and form new binding gels. It was a brilliant workaround born of necessity and careful observation. This was not a science understood in our modern, laboratory sense. A master mason did not speak of calcium-silicate-hydrate gels. He spoke of recipes passed from father to son, or guarded within the scriptorium of a monastery. He knew that mortar made with finely ground tile dust set harder underwater, that it seemed to gain strength with years rather than lose it. This practical, trial-and-error knowledge became embedded in the guild traditions, the unwritten laws of craft that built Europe. Manuscript copies of Vitruvius's 10 books on architecture did circulate among the learned, but for the majority of builders, the why was less important than the proven how. The result was a concrete that varied from region to region, its quality dependent on the local clays and the skill of the burn. It might not have possessed the legendary, monolithic endurance of a Roman harbor, but it was a material of remarkable resilience. The foundations of Durham Cathedral, laid upon such a mortar, have borne immense weight for nearly 1,000 years. The substructures of many medieval castles, constantly damp from moats or earth, often show less decay than the stonework above, precisely because these mortars could handle moisture in a way modern concrete cannot. This medieval chapter is a bridge, a 1,000-year-long whisper of a greater knowledge. It kept the flame alive not through perfect understanding, but through stubborn, practical ingenuity. It proves that the principle of a reactive, self-integrating binder was too powerful to be completely lost. Yet this bridge ultimately led to a cliff edge. For with the coming of the Renaissance and then the Industrial Revolution, this accumulated, localized wisdom would be swept aside in pursuit of something new, something fast, and something tragically brittle. This stubborn medieval ingenuity, however, was about to meet an irresistible force, the relentless speed of the industrial age. The world was building railways, factories, and skyscrapers, and it needed a stone that could be made to order, not one that required years of patient curing. The answer arrived in a bag of grey powder, patented in 1824 by an English bricklayer named Joseph Aspdin. He called it Portland cement, for its color resembled the prized building stone quarried on the Isle of Portland. This was not an evolution of the old recipes, it was a deliberate break from them. Aspdin's process was one of intense, controlled fire. He took limestone and clay and burned them together in a kiln at temperatures so high they fused into a new, artificial rock called clinker. This clinker was then ground into an incredibly fine powder. When mixed with water, this powder undergoes a rapid, exothermic chemical dance, forming a rigid, crystalline matrix with what builders call high early strength. It sets fast and it gets hard quickly. This was the perfect material for an era obsessed with progress and scale. It could be produced in vast, standardized batches in factories, shipped anywhere by rail, and used to pour foundations, columns, and beams on a timeline that would have been unthinkable to a medieval master mason. The modern city, with its soaring vertical landscapes and sprawling infrastructure, was literally poured from this substance. But this revolutionary speed came with a hidden, profound trade-off. To achieve that rapid, dependable hardening, the chemistry of Portland cement creates a very dense, low-porosity structure. Think of it as a meticulously assembled brick wall, with every unit tightly locked in place. It is immensely strong under compression, but it has very little give. It is brittle. This brittleness makes it vulnerable to the very stresses of the modern world it helped to build. As it cures, it undergoes shrinkage, pulling against itself. It expands and contracts with daily and seasonal temperature swings, a phenomenon called thermal stress. In a large structure, these forces have nowhere to go, and so the material cracks. These micro-cracks are the fatal flaw. In the ancient Roman mix, a crack was a site for healing, a trigger for new crystal growth. In modern concrete, a crack is a highway for destruction. It provides a direct path for water and oxygen to infiltrate the heart of the structure. And here lies the second part of the modern recipe, the hidden Achilles heel. To give concrete strength under tension, the kind of force that bends a beam, we embed steel reinforcement bars, or rebar, inside it. This marriage of steel and stone is what allows for the graceful bridges and cantilevered floors of our world. But when water seeps through those inevitable cracks, it reaches the steel. If that water carries dissolved salts, like the chlorides from road de-icing agents or from sea air, the corrosion process accelerates violently. The steel rusts, and rust occupies more volume than the original metal. This expansion creates tremendous internal pressure, literally bursting the concrete from the inside out in a process engineers call spalling. You have seen this, the crumbling, flaking patches on a bridge support or parking garage, with rusty rebar exposed like bones. This is the primary killer of modern concrete structures, a slow, inevitable decay written into the very chemistry of the material we trusted to be permanent. We traded a living, self-healing stone for a fast, strong, but ultimately mortal one. The question then becomes, having seen the limits of our own invention, can we look back across the centuries and recover not just the recipe but the philosophy? This silent, chemical partnership reveals another layer of the ancient secret, one often overlooked in the shadow of the famous mortar. Look closely at a chunk of Roman concrete, and you will see it is not a uniform gray paste. It is a mosaic, a carefully assembled landscape of larger stones and rubble embedded within the binding matrix. These are the aggregates, and their selection was not an afterthought. It was an act of profound geological intuition. Ancient builders understood that the stones themselves had to be part of the long-term conversation. They did not simply choose the hardest, cheapest rock they could find. They chose stones with a story. In Rome, the aggregate of choice was often tuff, a soft, lightweight stone born of volcanic eruptions. To a modern engineer focused on pure compressive strength, tuff might seem like a poor choice. It is porous and relatively weak, but that porosity was its genius. The tiny voids within each piece of tuff acted like a network of microscopic reservoirs, drawing in the alkaline lime Pozzolana slurry during mixing. More importantly, over decades and centuries, that same porous surface area provided a vast reactive interface. The soft, silica-rich tuff could slowly dissolve and interact with the binder, further weaving the entire mass, large stones and fine mortar alike, into a single, inseparable, monolithic whole. The aggregate was not just trapped in the concrete, it became chemically married to it. This stands in stark contrast to the aggregates in most modern mixes. Today, we typically use hard, dense, and chemically inert stones like granite or quartzite gravel. They are chosen for their mechanical strength, their uniformity, and their low cost. They create an excellent physical interlock, a sturdy skeleton within the cement paste, but they are silent partners. A piece of granite in modern concrete is essentially a closed book. Its hard, crystalline surface does not react with the surrounding cement. It sits there, strong but passive, contributing nothing to the long-term chemical life of the material. This creates a critical vulnerability. In the ancient system, the reactive volcanic ash in the mortar and the reactive volcanic rock in the aggregate created a distributed reservoir of silica throughout the entire material. Any crack that formed would, as it propagated, inevitably intersect more of this reactive material, fueling the self-healing process from multiple sources. In the modern system, once a crack passes through the brittle cement paste and reaches an inert aggregate, the healing conversation simply stops. The crack meets a dead end, but for the structure, that dead end is the beginning of failure. The aggregate becomes merely a boundary, not a participant. So we built a world from a dialogue of strangers, where the binder and the stone never truly learn to speak to one another across time. This fundamental disconnection in our material philosophy points to a deeper question, one that moves beyond chemistry and into the very mindset of the builders themselves. But what if the secret was not just in the ingredients, but in the very moment of their mixing? Modern concrete production is a model of cool, controlled precision. Ingredients are measured, water is added with exacting care, and the mixture churns in the rotating drum of a ready mix truck, arriving at the job site as a uniform, predictable slurry. It is a process designed for consistency, and in that consistency, we may have lost a vital spark. Recent scientific investigations have begun to uncover a fascinating and counterintuitive quirk in the Roman method, a detail so subtle it was missed for centuries. Using advanced tools like X-ray diffraction and electron microscopy, researchers have analyzed the microscopic structure of ancient concrete samples. What they found was startling. The Romans often did not use slaked lime, the stable, putty-like form we associate with traditional mortar. Instead, they frequently added quicklime directly into their mix. Quicklime, or calcium oxide, is a highly reactive powder created by roasting limestone in a hot kiln. To our modern sensibilities, this seems like a dangerous shortcut. When quicklime meets water, it does not simply dissolve. It undergoes a violent chemical slaking process, releasing intense heat and steam. It is exothermic, a reaction that can literally boil water. The Roman builders were essentially creating a hot mix, tossing these reactive white chunks in with the volcanic ash and wet aggregates. Imagine the scene, a cloud of steam rising from the mixing pit, the material itself growing warm to the touch as the quicklime particles greedily consumed moisture. This was not a tidy process, it was chaotic, hot, and alive, and that chaos, scientists now believe, was precisely the point. This internal heat bath did something remarkable. It encouraged the formation of unique, ultra-durable mineral phases within the concrete as it cured. Minerals with names like stretlingite and complex calcium-silicate-hydrates began to crystallize in this reactive environment. These are not the brittle crystals of modern cement. They are plate-like or fibrous minerals that act as reinforcing agents, filling spaces and creating a tougher, more resilient internal architecture. More importantly, the hot mix created a profoundly heterogeneous material from the very beginning. Not every particle of quicklime would have slaked at the same instant. Some would have remained as tiny, reactive white cores, encapsulated within the hardening concrete. These became long-term reservoirs of healing potential. Centuries later, if a crack allowed water to seep in, it could reach one of these dormant quicklime particles, restarting the slaking process on a microscopic scale. This would create a fresh, saturated solution of calcium-rich fluid right at the site of the damage, which would then precipitate as new healing crystals, seamlessly filling the gap. The Romans, through practical observation rather than laboratory science, had engineered a self-healing system with a built-in backup power supply. Their concrete was not just a finished product, it was a captured chemical reaction, paused in mid-flow, waiting for the right conditions to continue its work. This stands in total opposition to our modern, cool mix philosophy, where the goal is a completely spent, inert, and uniform paste. We strive for a material that is finished on day one. They created a material that was designed to never truly be finished. So we are left with a profound irony. Our most advanced analytical tools are now revealing that the superior material was born not from greater control, but from a deliberate embrace of a certain productive chaos. This revelation forces us to confront the final, and perhaps most human, layer of the mystery. This fundamental shift in philosophy is most clearly seen in our relationship with a simple, universal substance, water. For a modern engineer, water has a very specific and limited job. It is the agent of hydration, the liquid that triggers the chemical setting of the cement powder. Once that reaction is complete, ideally within the first 28 days, the water's work is done. Any water that enters the hardened structure afterward is viewed with suspicion, as an intruder, a corrosive force that brings freeze-thaw cycles and chloride ions to attack the steel within. We spend billions on sealants, membranes, and drainage systems in a perpetual war to keep water out. The ancient builders held a radically different view. To them, water was not just a starter, it was a lifelong partner. It played a dual role, first as the spark of creation, and then, for centuries afterward, as the circulatory system for perpetual repair. When Roman concrete cured, it did not use up all its potential. Tiny, white reservoirs of unreacted quicklime, those hot mix clasts, remained trapped inside the stony matrix. They sat dormant like seeds waiting for rain. Then, inevitably, a hairline crack would form. In our structures, this is the beginning of the end. In theirs, it was an invitation. As moisture from rain, humidity, or even seawater seeped into that microscopic fissure, it did something extraordinary. It sought out those dormant lime particles and began to dissolve them, creating a solution rich in calcium ions. This mineral-rich fluid traveled along the crack, a microscopic repair crew dispatched to the exact site of damage. Upon meeting carbon dioxide from the air diffusing into the same crack, a quiet miracle occurred. The calcium and carbonate ions combined, precipitating out as new, solid crystals of calcite, a form of limestone. Slowly, patiently, these crystals grew, filling the void from the walls inward, gluing the crack shut with a material nearly identical to the surrounding stone. The weakness had been transformed into a site of regeneration. Water was not the enemy, it was the delivery vehicle for the structure's own healing minerals. Medieval masons, working centuries later without this chemical understanding, witnessed the effects of this process firsthand. In the damp foundations of their cathedrals or in old Roman ruins, they would sometimes see a white, powdery efflorescence weeping from the joints or cracks. They called it lime sweat, and some attributed it to the stone's vital spirit or the lingering soul of the mortar. What they were observing was the visible evidence of that slow cycle geochemical process, the concrete's enduring conversation with water and air, still actively repairing itself long after its creators were gone. This reveals a breathtaking inversion of our modern logic. We design for a single, perfect moment of strength, then defend that perfection against a hostile world. They designed for an ongoing relationship with the world, building a material that grew stronger not in spite of the elements but because of them. The crack was not a failure, it was part of the design. The most powerful proof of this ancient wisdom is found where modern engineering often fails beneath the waves. While we struggle to build seawalls that last 50 years, the Romans constructed harbors that have withstood 2 millennia of relentless saltwater assault. Take the submerged concrete piers of Caesarea Maritima, a colossal port built by Herod the Great on the Mediterranean coast. For 2,000 years, these structures have been pounded by storms, scoured by abrasive sand, and bathed in a corrosive brine that eats modern steel reinforced concrete from the inside out. Yet when marine archaeologists and materials scientists finally examined them, they found something astonishing. The concrete was not merely surviving, it was thriving. Core samples extracted from these ancient piers revealed a material that had grown stronger and more cohesive over the centuries, its internal structure transformed by the very element meant to destroy it. This is where the philosophy of partnership becomes a physical, chemical reality. Modern marine concrete is engaged in a constant, losing battle. The chlorides in seawater penetrate the smallest crack, traveling until they reach the steel rebar inside. A destructive electrochemical reaction begins, rusting the metal. As the rust expands, it exerts tremendous pressure, bursting the concrete apart in a process called spalling. You can see the tragic results on any aging coastal bridge or pier, with crumbling patches and rusty steel tendons exposed like broken bones. The Roman approach was the polar opposite. Their marine concrete had no steel to protect. Instead, its mix of volcanic ash and lime was designed to welcome the seawater, to begin a new and beneficial chemical conversation. When saltwater infiltrated the porous concrete, it did not find a passive victim. It found a highly reactive environment. The alkaline lime and the silica-rich volcanic ash began to interact with the dissolved minerals in the seawater, particularly magnesium. Over decades and centuries, this slow-motion reaction precipitated rare, plate-like minerals with names like aluminous tobermorite and philipsite. These are not weak byproducts, they are exceptionally durable crystals that form interlocking, reinforcing layers within the material's fabric. They effectively fill pores and microcracks, making the concrete denser and more fracture-resistant over time. In essence, the seawater became a key ingredient in a curing process that never stopped. The harbor at Portus Cosanus, another Roman site, shows the same remarkable adaptation. Its breakwaters, constantly lashed by the Tyrrhenian Sea, are monuments to this intelligent design. The concrete there is not a relic frozen in time. It is a material that has been actively evolving, using the energy of the ocean to continuously remodel and reinforce itself at a microscopic level. This case study illuminates the core philosophical divide. We see the environment as an adversary to be walled out, leading us to design brittle, defensive structures with a built-in expiration date. The Romans saw the environment as a partner, even a collaborator. They engineered a material that could metabolize the forces arrayed against it, turning potential agents of decay into architects of longevity. Their concrete did not merely endure the sea, it was perfected by it. This architectural choice reveals a deeper truth about their priorities. The Romans built a world without steel skeletons. Their concrete, that self-healing volcanic stone, was almost always used in one specific way, in compression. Think of a stone in an arch, pushed downward by the weight above, its strength coming from being squeezed, not pulled apart. They mastered this principle, creating vast, open spaces like the interior of the Pantheon with its breathtaking, coffered dome. They did this not by embedding metal rods to resist tension, the pulling force that wants to bend a beam, but through pure, brilliant geometry and a profound understanding of their material's nature. The Pantheon's dome is a perfect hemisphere, a shape that channels all its immense weight downward into the supporting drum wall, and as the dome rises, the concrete mix itself changes. At the base, they used heavy travertine aggregate, but layer by layer they incorporated lighter materials like porous volcanic tuff and even empty clay amphorae at the very top. This was a deliberate lightening, reducing the load on the lower sections without sacrificing structural integrity. The result was a monument that relied entirely on the mass and the form of the concrete itself. This stands in absolute contrast to our modern world. Our concrete is almost never alone. We embed steel reinforcement bars, rebar, within it to give it tensile strength, allowing us to create the slender beams, cantilevered balconies, and soaring, thin shell structures that define contemporary architecture. This marriage of steel and stone enabled our cities to reach for the sky, but it also introduced a fatal, hidden partnership. Concrete is alkaline, which initially forms a protective passivation layer around the steel, shielding it from rust. But this shield is fragile. The moment a crack forms, and they always do from shrinkage or stress, it creates a highway for moisture and oxygen. In marine environments or on roads treated with de-icing salts, chloride ions hitch a ride on that moisture. When they reach the steel, they break down the passivation layer and corrosion begins. The chemistry of rust is brutally simple, iron reacting with oxygen and water to form iron oxide. But this new compound occupies much more volume than the original steel. It swells with immense, inexorable force, exerting pressures so great they can literally burst the hard concrete from the inside out. You have seen the evidence, the spalling and flaking on bridge supports, with rusty rebar exposed like the bones of a decaying giant. This is the primary failure mode of modern concrete, a built-in obsolescence written into its very design. The ancient builders avoided this entirely. Their material only had to be durable in itself. It did not have to serve as a protective shell for a vulnerable metal core that would one day betray it. Their paradigm was different, favoring longevity and monolithic endurance over maximum span or minimal material use. They built for the forever of stone, not the scheduled lifespan of a steel-reinforced beam. This fundamental difference forces us to ask a difficult question about our own values. What have we sacrificed in our relentless pursuit of height and efficiency? And is there a way to marry the wisdom of the past with the ambitions of the present? The Pantheon did not need a maintenance schedule. Its strength was not a race to a finish line, but a slow, patient climb toward an ever more distant horizon. This difference between ancient and modern concrete is more than a chemical footnote. It is a mirror reflecting two opposing philosophies of time and value, of what we believe strength truly means. The Roman builder and the medieval mason after him operated on a generational timescale. When they mixed their hot lime with volcanic ash or crushed brick, they were not just solving a problem for that year or even for their own lifetime. They were planting a seed in stone, initiating a chemical process they knew would outlive them by centuries. Their investment was in permanence, in legacy. The concrete in the foundations of a cathedral or an aqueduct was meant to become part of the land itself, a gift to an unknown future. Its strength was slow strength, a quality that grew not in days but in decades as water and air continued the quiet work of crystallization and repair. This mindset was built into the culture. A project could take 100 years, spanning the careers of multiple master builders, each adding to the vision of the first. The value was in the endurance of the thing created, a testament to the community that built it. Our modern world operates on a different clock. It is the clock of economic cycles, of rapid urbanization, and of immediate return on investment. When we pour concrete today, we measure its success against a universal standard, the 28-day strength test. If it meets a specific compressive strength by that date, it is certified and construction races ahead. This is fast strength. It is the engine of our progress, allowing us to erect cities in years instead of centuries. It is efficient, predictable, and perfectly suited to the pace of contemporary life and finance. But this focus on short-term metrics can obscure long-term costs. A material that is declared strong at 28 days may, in fact, be on a hidden path to premature aging. Its brittle nature, its vulnerability to cracking and corrosion, means its true lifespan might be measured in decades, not millennia. This can foster a disposable infrastructure mindset, where repair and replacement are baked into the economic model. We build bridges with 50-year design lives, knowing they will require immense reinvestment by the next generation. The question this invites is profound. Which society is truly stronger, the one that builds a few things to last 1,000 years, or the one that builds thousands of things that last 50? The ancient approach asked more of its builders. It required deep, localized knowledge, patience, and a willingness to invest in materials and processes whose full benefit they would never see. Our approach asks something different of us. It demands global supply chains, relentless innovation, and the ability to house and connect billions of people quickly. Neither philosophy is purely right or wrong, but they exist in a stark and telling tension. One sees time as a collaborator, the other as a competitor to be beaten. As we face global challenges of resource scarcity and environmental cost, this contrast becomes urgently relevant. The crumbling overpass and the eternal dome are not just two objects, they are two answers to the same eternal human question. How do we build a world worthy of the future? That generational patience extended to the very earth beneath their feet. Ancient builders did not simply use local materials, they engaged in a deep dialogue with their landscape. Every structure began not on a blueprint, but in the geology of the place itself. The volcanic ash that made Roman concrete so miraculous was not a global commodity. It was the dust of nearby eruptions, the literal ground of their world transformed into eternal stone. Lime was burned in kilns fed by local wood, using limestone from regional outcrops. The aggregates, whether tuff or rubble, came from quarries a cart ride away or were salvaged from older buildings on the very same site. This was not sustainability as a conscious philosophy. It was sustainability as the only possible reality. The supply chain was the horizon you could see from the top of the hill. This hyper-local sourcing created a profound and often overlooked advantage: material acclimation. The concrete born from a specific volcano, mixed with water from a local spring, and built with stones from a nearby riverbed was inherently tuned to its environment. It had already begun its chemical conversation with the local climate, minerals, and humidity before the first block was laid. It was a product of its place, designed to endure the very conditions that created its ingredients. Medieval monastic communities exemplified this principle perfectly. A monastery was often a self-contained world. The brothers would clear the land for their foundation, and the very stones they pulled from the earth became the rubble for their footings. They would build a lime kiln on site, burning local limestone with charcoal from their own woods to produce the binder for their mortar. The entire cycle of creation, from raw earth to sacred space, happened within a closed, mindful loop. The energy invested was human and animal. The transportation was measured in footsteps, and the result was a building that felt rooted, as if it had grown from the soil rather than been imposed upon it. Now hold that image in your mind and contrast it with the birth of a modern concrete slab. The Portland cement likely began as limestone mined in one country, shipped to another for processing in a fossil fuel-fired kiln, then transported again as a powder to a mixing plant. The sand and gravel aggregate may come from a riverbed or quarry hundreds of miles distant, hauled by diesel truck or freighter. The water is municipal, treated and piped. These components, strangers from across the globe, are blended into a homogeneous slurry and poured into a form. This process is a triumph of globalization and industrial efficiency, allowing us to build the same skyscraper in Dubai, New York, or Singapore. But it comes with a staggering hidden cost, a carbon footprint so large that concrete production is now one of the single largest sources of human-made carbon dioxide emissions worldwide. We expend an ocean of ancient energy, burn mountains of fuel for transport, and release gigatons of greenhouse gases to create a material that, in many of our most critical applications, we expect to maintain and repair within 50 years. This is the modern paradox, a material of such immense embedded energy and environmental cost, designed for a lifespan that is often shockingly brief. We have mastered the logistics of global construction, but we have severed the vital, strengthening bond between a building and the land that holds it up. The ancient builder's constraint, his limited range, was in fact the source of his material's profound resilience. Our liberation from that constraint has given us the world, but it has also given us a substance that often feels alien to its own foundation, and a sustainability crisis written in gray powder and rusting steel. The same rain that gently polished Roman marble for centuries can spell ruin for a modern bridge in a single generation. This paradox centers on a quiet chemical process called carbonation, a meeting of stone and sky that reveals how a single natural force can be both a healer and a destroyer, depending entirely on what we have built. At its heart, carbonation is the reaction between calcium hydroxide, a leftover from the lime in concrete, and carbon dioxide from the air. They combine to form calcite, a stable form of limestone. In the ancient world, this was a slow, patient gift. Their concrete was highly porous, allowing air and moisture to circulate deep within its matrix. When a microcrack formed, carbon dioxide could diffuse in, meet the abundant free lime, and precipitate new calcite crystals directly inside the fissure. It was a built-in repair mechanism, a way for the atmosphere itself to gently stitch small wounds closed over decades. This process never truly stopped, contributing to that legendary increase in strength over centuries. The material was in a lifelong, gentle conversation with the very air around it. But in our modern reinforced concrete, this same conversation becomes a silent, corrosive whisper. Our mixes are designed to be less porous, more dense and watertight, which ironically can accelerate a dangerous form of surface carbonation. Carbon dioxide from the air slowly penetrates this hardened paste, reacting with the calcium hydroxide and neutralizing it. This steadily lowers the pH of the concrete, reducing its alkalinity, and here lies the catastrophe. That high alkalinity is the only thing protecting the steel rebar buried inside. It creates a thin, stable passivation layer on the steel surface, a chemical shield that prevents rust. As carbonation advances like an invisible front through the concrete, it destroys this shield. By the time the carbonation depth reaches the steel, the protective environment is gone. the rebar is left naked and vulnerable in a now neutral, damp environment. Then the smallest ingress of water and oxygen triggers corrosion. The steel rusts, expands, and begins to burst the concrete apart from within. So the very same atmospheric process that patiently healed the cracks in a Roman harbor becomes the stealthy trigger for the collapse of a modern parking garage. Carbonation is not inherently good or evil, it is simply chemistry. The outcome is determined by our design. We took a material system that worked in harmony with this natural process and fundamentally altered it by embedding a hidden weakness, a metal core that cannot survive without a specific chemical environment. The ancient builders avoided this trap entirely by designing a monolithic material that welcomed the air, a stone that could breathe and grow stronger from it. Our innovation gave us unimaginable spans and slender forms, but it also made our structures dependent on a fragile, impermanent shield, one that the slow breath of the atmosphere is destined to dissolve. The silent conversation between ancient stone and modern air is no longer a mystery lost to time. In laboratories from Cambridge to California, a quiet revolution is underway. Armed with tools of astonishing precision, like electron microprobes that can map a single grain of sand and synchrotron radiation that reveals the atomic dance within a speck of mortar, scientists have become detectives of durability. Their mission to reverse engineer a 2,000-year-old technology and finally understand its language. Teams from institutions like MIT and the University of California, Berkeley, have published groundbreaking studies that move beyond speculation. They have physically confirmed at the microscopic level the genius of the Roman system. Those white lime clasts once seen as imperfections are now celebrated as a deliberate, built-in repair network. The rare plate-like minerals found in seawater concrete, like aluminous tobermorite, are no longer curiosities but blueprints for resilience. This research has shifted the entire conversation from historical admiration to active, urgent innovation. The goal is no longer just to understand the past, but to build a better future with its wisdom. This has given rise to a new field, bio-inspired or self-healing concrete. Imagine a material for the 21st century that doesn't just sit there and decay, but actively responds to damage, much like skin healing a cut. Researchers are exploring astonishing pathways to achieve this. Some are developing synthetic microfibers that act as a distributed nervous system within the concrete, sensing cracks and releasing stored adhesives. Others are working with specially selected bacteria, encapsulated and dormant within the mix. When a crack forms and water infiltrates, these tiny organisms awaken, consuming nutrients provided in the design and precipitating new calcite, literally growing new stone to seal the breach. Another approach involves embedding tiny, brittle capsules filled with silica-based healing agents. When a crack propagates, it breaks the capsules, releasing their contents to react and form a solid plug. Each of these methods is a modern echo of an ancient principle, the idea of a material with a built-in immune system. It is a profound full-circle moment. For centuries, we viewed the self-healing of Roman concrete as a magical artifact, a lost secret. Now, we understand it as a sophisticated materials science strategy, one that we are desperately trying to replicate with our own advanced tools. The story is no longer about a forgotten past, but about a recovered philosophy guiding our next great leap. The question is no longer what they knew, but how quickly we can learn to build with that same foresight. The laboratory breakthroughs present a tantalizing future, but the path from scientific paper to building site is paved with formidable obstacles. Translating the ancient philosophy of slow strength into our modern, high-speed world runs headlong into the colossal machinery of the global construction industry. This is a trillion-dollar ecosystem engineered for one thing above all else: predictable efficiency. Its lifeblood is Portland cement, a material with a known 28-day strength, a standardized global specification, and a supply chain that operates like clockwork. Introducing a material that cures over years, not weeks, and whose performance depends on the unique chemistry of local volcanic ash or manufactured pozzolans, is like asking a Formula One pit crew to switch to maintaining a centuries-old sailing ship. The entire economic model would shudder. Construction projects are financed on tight schedules, where delays cost staggering sums in interest and lost revenue. A concrete that gains its true strength over decades offers no financial advantage on a quarterly report. The profit motive is aligned with fast strength, with pouring the next floor, opening the next bridge. The ancient model requires a radical shift in perspective, valuing long-term public savings and durability over short-term private gain. Then come the gatekeepers of safety, the building codes. These thick volumes of regulations are written around the known behaviors of modern materials, proving that a new, slow-curing pozzolanic concrete is safe for a 50-story building or a critical bridge would require years, perhaps decades, of testing and certification. The liability landscape is another minefield. Engineers and contractors rely on insurance policies based on established practices. Who assumes the risk if a structure using a novel, ancient-inspired concrete shows a different behavior in year 30? The chain of responsibility, from material supplier to architect to builder, is built for the known, not the experimental. Furthermore, the Roman recipe relied on a specific geology. True pozzolana from volcanic regions is not evenly distributed around the planet. We cannot rebuild the modern world using only the ash from Italian volcanoes. A literal, global revival of Roman concrete is therefore a logistical impossibility. But this is not the point of the discovery. The true value lies not in copying the recipe, but in adopting the principle. The goal is not to abandon Portland cement, but to transform it. The research into self-healing mechanisms, whether through bacteria, microcapsules, or engineered mineral reactions, is about embedding the ancient philosophy of resilience into the modern material. It is about creating a new generation of composite cements that use industrial byproducts, like fly ash from coal plants or slag from steel production, as modern pozzolans. These materials can mimic the beneficial reactions, reducing the carbon footprint while enhancing durability. The challenge, then, is not merely scientific but systemic. It requires us to redesign not just our concrete but our incentives. Can building codes be rewritten to reward 100-year lifespans instead of just minimum 28-day strength? Can the true cost of maintenance and replacement be factored into the initial price of a structure, making the higher upfront cost of a smarter material the obvious economic choice? The ancient builders worked within the constraints of their local landscape and a generational timeline. Our constraint is the inertia of a global system optimized for speed. The real test of our ingenuity will be whether we can build a new system, one that values the patience of stone in the age of the silicon chip. Perhaps the most elegant modern echo of the ancient philosophy is not found in a laboratory Petri dish, but in a power plant's waste pile. Geopolymer concrete represents a brilliant, full-circle homage to the Roman insight, using the discarded materials of our industrial age to forge a new kind of stone. At its core, the concept is strikingly familiar. Just as Roman builders used reactive volcanic ash, geopolymers use aluminosilicate materials, often industrial byproducts like fly ash from coal combustion or slag from steel production. These are not inert fillers, they are fine, glassy powders rich in silica and alumina, possessing a latent energy, a chemical potential waiting to be unlocked. The key that unlocks them is not slaked lime, but a strong alkaline activator, typically a solution of sodium silicate or potassium hydroxide. When this activator meets the fly ash or slag, it initiates a rapid polymerization reaction. Think of it not as a hydration process like Portland cement, but as a molecular chain linking event where the silica and alumina atoms in the waste materials dissolve and reassemble into a dense, three-dimensional network. This creates an incredibly strong, often more chemically resistant binder than ordinary cement, and it does so with a radically different environmental story. The production of Portland cement requires roasting limestone at nearly 2,500 degrees Fahrenheit, a process that releases carbon dioxide both from the burning of fuels and from the limestone itself as it decomposes. It is one of the largest industrial sources of greenhouse gases on the planet. Geopolymer concrete sidesteps this entirely. It uses materials that are already cooked. The fly ash is a byproduct of existing combustion, and the slag is a byproduct of existing steelmaking. By activating these wastes, we are not creating new emissions. We are sequestering and transforming existing industrial streams into something of profound value. The result is a concrete with a carbon footprint that can be 60 to 80% lower than its conventional counterpart, but the homage goes deeper than just sustainability. Some geopolymer formulations, under the right conditions, have been observed to exhibit a form of self-healing. If a crack forms, the highly alkaline environment within the material can slowly dissolve remaining unreacted particles, allowing new gels to precipitate and fill the gap, a process eerily reminiscent of the ancient Roman mechanism. This is not a direct copy of the 2,000-year-old recipe. It is something arguably more sophisticated, a technological leap that fully embraces the ancient principle. The Romans looked at a volcano and saw a binder. We are learning to look at our industrial landscape and see not just waste, but the raw ingredients for a new architectural era. Geopolymers move us toward a future where concrete is no longer a major contributor to our environmental challenges, but a potential part of the solution, a material that is high performance, durable, and born from a philosophy of circularity that even the master builders of Rome would recognize as wisdom. That commitment to ongoing care was woven into the very identity of the places they built. A medieval cathedral was never truly finished. Its completion was not a date on a calendar, but a state of becoming that stretched across generations. The master mason who laid the foundation stones knew he would not see the spire touch the sky. His son or his son's apprentice would carry the work forward. This created a profound, institutional mindset where maintenance was not an emergency response, but a sacred duty, a thread in the continuous tapestry of the community's life. Guilds of masons, carpenters, and lead workers were not just construction crews. They were the permanent guardians of the structure. They maintained detailed logs, passed down through oral tradition and later in written accounts, noting where a particular arch had always shown a hairline fissure in winter, or which section of roof valley tended to collect water. They watched the building breathe and settle with the seasons, treating it not as a static object, but as a living entity in dialogue with the earth and sky. When a crack was observed, it was not ignored until it became a threat. It was carefully monitored, often marked with a simple chalk line to see if it widened over the year. Repairs were made with an understanding of the original fabric, using compatible mortars and techniques. Leaking roofs were meticulously re-leaded, a costly but essential investment to protect the delicate stone vaulting and painted interiors within. Foundations were shored up with buttresses, not as an admission of failure, but as an intelligent adaptation to newly understood loads or shifting ground. This was preventative, attentive care, a form of stewardship that viewed time as a partner to be managed, not an enemy to be defeated. Contrast this with the modern cycle we often see today. Our engineering marvels are frequently designed, built, and then handed over with an implicit assumption of minimal upkeep. Budgets prioritize dazzling new construction over the unglamorous, ongoing work of preservation. Maintenance is deferred year after year until a leak becomes a flood, a crack becomes a structural alert, and a simple, affordable repair balloons into a multi-million-dollar emergency restoration project. We adopt a build-it-and-forget-it mentality, treating our infrastructure as disposable appliances with a warranty that eventually expires. The lesson from the medieval workshop is starkly clear. The legendary longevity of historical structures is not solely a triumph of material science. It is the product of a powerful partnership between resilient materials and an even more resilient human commitment to stewardship. The lime mortar could heal itself to a point, but the mason's watchful eye and timely intervention ensured that small issues never grew large enough to overwhelm that natural process. The lead roof kept the water out, but it was the roofer's generational knowledge that ensured the seams stayed sealed decade after decade. This partnership reminds us of an uncomfortable but vital truth. No material, no matter how self-healing or ingeniously formulated, is truly maintenance-free. Stone erodes, metal fatigues, wood rots, the environment is relentless. The choice is not between maintenance and no maintenance. It is between the small, steady, respectful care that prolongs life for centuries and the costly, traumatic crisis management that merely postpones collapse for a few more years. In the end, that medieval mindset reflects a deeper cultural value, that care is a form of respect. It is a declaration that what we build is worthy of our continued attention, that it is a gift to the future, not a burden to be abandoned. Their cathedrals stood not just because of the stone, but because of the promise made by each generation to the last, a promise to keep watch. Their promise to keep watch extended beyond the stone itself, into the very air within the walls. Ancient builders understood something we often engineer out, that the mass of a building could be a partner in comfort and longevity. Walk into the ruins of a Roman bath complex on a hot afternoon, and you will feel a deep, cool stillness. Step into the great hall of a medieval castle in the depths of winter, and you might find it surprisingly temperate despite the howling wind outside. This was no accident of thick walls. It was a deliberate performance by the material, a phenomenon called thermal mass. The colossal walls of Roman concrete or medieval stone acted like a giant, slow-breathing battery for heat. During the day, the sun's energy would be absorbed into the massive fabric of the building, but only very slowly, preventing the interior from rapidly overheating. Then, as night fell and the air cooled, that stored warmth would gently radiate back inward, taking the edge off the chill. This created a remarkably stable microclimate inside, a buffer against the wild swings of the external world. This environmental conditioning did more than just keep people comfortable. It directly protected the material itself. Modern thin shell concrete structures, especially those with extensive steel reinforcement, live in a state of constant, stressful motion. On a sunny day, the surface of a bridge or a building facade can become scorching hot, causing the concrete and the embedded steel to expand. At night, it contracts as it cools. This daily expansion and contraction, known as thermal cycling, is a relentless force. In a material that is brittle and filled with reinforcement, this repeated flexing contributes directly to the formation of microcracks. Each tiny fissure is another invitation for moisture, another breach in the defense. The ancient approach elegantly sidestepped this problem. By using vast quantities of material to create that thermal mass, they inherently dampened those temperature swings within the wall itself. The exterior surface might heat and cool, but the deep core of the wall remained at a far more stable temperature. This reduced the internal thermal stresses to a minimum, giving the concrete a peaceful, stable environment in which to perform its slow chemistry. The material was not fighting the climate, it was using the climate's own rhythms to maintain its equilibrium. This represents a profound holistic design, where the building's structural material, its environmental function, and its own long-term durability were all parts of a single, integrated system. The wall was not just a barrier, it was a climate moderator and a guardian of its own integrity. We are, in many ways, just beginning to recapture this wisdom. Our modern passive house standards and high-performance building designs prioritize thermal mass for energy efficiency, using materials like concrete, stone, or rammed earth to stabilize interior temperatures without mechanical systems. It is a return to that ancient principle, recognizing that the most resilient building is one that forms a symbiotic relationship with its environment, where the structure's very substance works to create the conditions for its own enduring strength. That deep thermal stability allowed the material to age not as a flaw but as a feature. We can see this in our own reactions to the passage of time on stone. The warm, mottled patina on a Roman aqueduct or the soft, mossy stains on a medieval wall are not viewed as decay. We see them as beauty, as the authentic signature of history, a narrative written by centuries of sun, rain, and air. This weathering is proof of endurance, a visual record of a dialogue between the built world and the natural one. We travel across continents to photograph these textures, valuing every crack and discoloration as part of the object's true character. Yet cast that same gaze upon a modern overpass or a concrete parking garage. A dark stain from a water leak is not charming, it is alarming. A network of hairline cracks in a sidewalk is not a story, it is a liability. We have culturally redefined what aging means for our own creations. For ancient structures, patina equals authenticity. For modern infrastructure, patina equals failure. This shift in perception drives a profound difference in how we care for what we build. Our modern mindset is often one of cosmetic panic. The moment a stain or crack appears on a concrete surface, the immediate impulse is to cover it up, to erase the visible evidence of time. This leads to maintenance practices focused on the symptom, not the cause. A stained concrete facade might be pressure washed or painted with a sealant to restore its uniform gray appearance. But if that sealant traps moisture inside the wall, it can actually accelerate the very decay it was meant to hide, forcing water to migrate elsewhere and cause new, hidden damage. Similarly, cracks are often filled with rigid, non-breathing epoxies that look tidy but do not allow for the natural movement of the structure. When the concrete inevitably expands or contracts with the next season, it stresses against that rigid patch, often creating new, larger cracks right beside the repair. We treat the visual blemish as the problem, rather than listening to what it is telling us about the structure's health. The ancient and medieval world, you seem to possess a greater acceptance of a material's natural life cycle. They understood that stone would wear, that mortar would weather, and that a building would settle into the land over generations. Their maintenance was less about preserving a pristine, factory-fresh appearance, and more about managing this inevitable process with respect. Repairs were made with compatible, breathable materials that worked with the original fabric, not against it. A patch of new mortar on an old wall was not meant to be invisible. It was meant to be sympathetic, a visible but honest record of care across time. This attitude points toward a more sustainable philosophy for today. What if we designed and maintained our infrastructure with the expectation that it will change visually, that it will show its age in a graceful way? This would require selecting materials that weather well and designing details that allow water to drain clearly rather than stain secretly. It would mean monitoring cracks to understand their behavior before automatically sealing them, and using repair materials that are chemically and mechanically compatible, even if they don't create a perfect color match. It is about shifting from a fear of decay to an understanding of patina, from seeing time as an enemy that must be defied to recognizing it as a force that can be guided. The green stain of copper on a roof is beautiful, the rust on a steel beam is catastrophic. The choice of material and the expectation of its aging are two sides of the same coin. By learning to appreciate the honest weathering of our own constructions, we might just build things worthy of acquiring a noble patina rather than a shameful stain. Even the masters of stone sometimes heard it crack. For all its legendary resilience, ancient concrete was not a magic spell granting invulnerability. Its history is punctuated by collapses and settlements, moments where ambition outpaced understanding, or where the silent earth below refused to cooperate. These failures are not stains on the record, but essential chapters in the manual, teaching us where the boundaries of that ancient wisdom truly lay. Take the immense Basilica of Maxentius in Rome. Its soaring central nave, wider than that of St. Peter's, was a breathtaking feat, yet a significant portion of its vault collapsed in antiquity. Modern analysis suggests why. The builders, pushing the limits of span and height, may have used a concrete mix with an aggregate that was too heavy for the ambitious design. Or perhaps the curing process was rushed in the political urgency to complete an imperial project. The material, though excellent, was asked to do something beyond its carefully tuned parameters. Similarly, the mighty Colosseum itself has experienced noticeable settling over the centuries, a tilt visible to the careful observer. This was not a failure of the concrete in the walls, but of the foundation beneath them. The structure was built on a former lake bed, on soft, alluvial soil. While Roman engineers were adept at creating deep pilings and drainage, the immense, uneven weight of the elliptical amphitheater ultimately led to differential settlement. The lesson is clear: even the most perfect material cannot compensate for an unwilling foundation. Later periods, especially during times of economic or political strain, provide another kind of lesson. In some repairs or hurried constructions, inferior materials were substituted. A mortar might be made with less reactive ash or with poorly slaked lime. These patches, these later additions, are often the first to crumble in an otherwise sound ruin, showing that the practitioners themselves understood the recipe's delicate balance. When they cut corners, the material told on them, decades or centuries later. This historical record of fracture and settlement is profoundly instructive. It tells us that the Romans and medieval builders were not wizards. They were brilliant engineers working with a deep but not infinite understanding. Their monumental successes occurred when they respected the dialogue between material, form, and site. They built thick walls for tall structures. They used lighter aggregates at the tops of domes, and they invested immense labor in foundations when the ground was suspect. Their triumphs came from working within the understood limits of their materials' conversation with the world. In our modern era, driven by the desire for ever more daring architectural spectacle, we sometimes forget this principle. We push materials to their absolute tensile limits, relying on complex calculations and steel reinforcement to achieve forms that defy gravity. The ancient failures whisper a caution that every material has a language, a way it wants to bear weight and handle stress. Ignoring that language, whether in the pursuit of imperial glory or contemporary awe, invites nature to write its own correction in the ledger of stone. Studying these ancient collapses does not diminish their achievement, it humanizes it. It turns their concrete from a mythical artifact into a mastered technology, with a learning curve written in rubble as well as in enduring wonder. Their legacy, therefore, is not just a recipe for a self-healing mix, but a philosophy of building that listens, that respects constraints, and that knows true innovation lies not in defying nature's rules, but in learning to speak her language with greater fluency. The stone was never just a stone. For a Roman engineer, the volcanic concrete rising from his mixing pit was more than a building block. It was a physical declaration. It spoke of an empire that believed its order was as enduring as the mountains, a civilization that built aqueducts and harbors not for a generation, but for eternity. The material itself became a symbol of Roma Aeterna, eternal Rome. Its slow, self-healing strength was not just a practical advantage, it was a philosophical necessity, a way to make the abstract ideal of permanence tangible in the world. This symbolic weight directly shaped every aspect of its use. Only the most durable, reactive mixes were worthy of an imperial forum or a temple to the gods. The care in its crafting was a form of reverence, an act of aligning human ambition with the timeless cycles of geology. Centuries later, medieval masons building a cathedral were engaged in a similar act of symbolic construction. Their mortar, mixed with the crushed remnants of older holy sites or carefully formulated pozzolans, was meant to bind more than stone. It was meant to bind earth to heaven. The cathedral was a vision of divine permanence made solid, a promise in limestone and mortar that faith would outlast any king or crisis. The material had to be worthy of that promise. Its resilience was not an engineering feature, it was a theological statement. The master mason knew his work would stand for centuries, a legacy for a community he would never meet, and so he built with a mindset of sacred stewardship. This cultural framing created a powerful feedback loop. The belief that a structure should last forever motivated the search for the most enduring materials, and the existence of those enduring materials reinforced the cultural belief in permanence. It was a self-fulfilling prophecy carved in stone. Now, shift your gaze to the concrete landscape of the 20th and 21st centuries. How do we culturally perceive the material that shapes our daily world? For many, modern concrete evokes something very different. It is the raw, exposed facade of a brutalist university building, often described as cold or imposing. It is the crumbling underbelly of a multi-story parking garage, stained by water and scarred by salt. It is the anonymous foundation of a suburban home, poured quickly and hidden from view. In our common language, concrete has become synonymous with the utilitarian, the cheap, and the temporary. We speak of concrete jungles, not concrete gardens. This cultural devaluation is subtle, but its consequences are profound. When a material is seen primarily as a cost-effective means to an end, the incentives shift dramatically. The focus in specification moves toward initial price and short-term strength, not toward century-long resilience. The construction timeline prioritizes speed of pouring over the patience of proper curing. Maintenance becomes an afterthought, a budgetary line item to be minimized, because why invest heavily in preserving something viewed as inherently disposable or easily replaced? We have, in a sense, broken the symbolic feedback loop. We no longer build courthouses or libraries or homes with a foundational belief that they must speak to the people of the year 2100. We build them to meet a budget and a code for today. This mindset may be the single greatest obstacle to creating a built environment that lasts. For if we do not believe our creations are worthy of legacy, we will never allocate the resources, the care, or the innovation needed to make them legacy-worthy. The chemical recipe for self-healing concrete is a triumph of laboratory science, but the will to use it is a question of cultural values, reconnecting with the idea that our infrastructure, our public spaces, and even our homes are cultural artifacts in the making could change everything. Imagine if we poured the foundation of a new school with the same symbolic intention as a medieval mason laying the cornerstone of a cathedral, with the understanding that children not yet born would learn within its walls. That shift in perspective, from seeing concrete as a consumable product to seeing it as the literal groundwork of our collective future, could motivate the specifications, the budgets, and the meticulous care required to build for the long now. The most durable material in the world cannot save a structure that we have already decided, in our hearts, is not built to save. The search for a better concrete has led to a profound historical irony. We are now turning to the waste products of our own industrial age to rediscover the reactive magic of ancient pozzolans. These modern materials have a technical name, supplementary cementitious materials, but their story is one of redemption. Fly ash, the fine powder left over from burning coal in power plants, was once just a problematic waste piled in lagoons or landfills. Ground granulated blast furnace slag, a glassy granular material from steel production, was similarly discarded. And silica fume, an ultrafine dust collected from the production of silicon metal, was considered a nuisance, yet under the microscope, these substances reveal their secret. They are rich in amorphous silica, the same highly reactive, glassy form found in the volcanic ash of Italy. When added to modern concrete mixes, they do precisely what the ancient Pozzolans did. They react with the lime byproducts of Portland cement hydration, forming additional calcium-silicate-hydrate gel, the same strengthening and densifying binder. This is not a minor improvement, it is a transformation of the material's very nature. Concrete made with these supplementary materials develops greater long-term strength, becomes significantly less permeable to water and harmful chlorides, and exhibits better resistance to the chemical attacks that plague ordinary mixes. It is, in essence, a hybrid, marrying the rapid initial set of modern cement with the slow, strengthening Pozzolanic dialogue of the ancient world, but the benefits extend far beyond performance. Using fly ash or slag replaces a portion of the Portland cement clinker, the most carbon-intensive ingredient. This can cut the carbon footprint of a concrete mix by 30, 50, even 70%. We are taking the literal dust of our fossil fuel economy and our heavy industry, and we are transmuting it into durable, climate-friendly stone. This is a powerful step toward a circular economy, where waste is not an endpoint but the beginning of the next cycle of creation. It suggests a hopeful path forward, one where the relentless engine of industry that gave us brittle concrete might also provide the key to its own redemption, by offering up the very materials needed to build something more enduring. This artisanal wisdom was both its genius and its greatest vulnerability. The Roman structor or master builder carried his recipe not in a printed manual, but in his hands and his memory. He knew that the volcanic ash from the hills outside Rome had a different character than the ash from the Bay of Naples. The lime burned from local limestone in Gaul would behave differently than that from the quarries of Tivoli. His craft was one of constant, subtle adaptation. He would test a pinch of ash on his tongue for grit, judge the slaking of the lime by its heat and texture, and adjust his proportions based on the sand from the nearby riverbed. The concrete that rose from his worksite was a unique product of that place, that moment, and that man's accumulated experience. This deep, localized knowledge created structures perfectly tuned to their environment, but it also meant that the secret of Roman concrete was not a single formula. It was 10,000 variations, each brilliant in its context, but each dying with the master who held it. This stands in absolute opposition to the foundational principle of modern civil engineering, standardization. We build a world that demands predictability. A bridge in Seattle must meet the same safety codes as a bridge in Singapore. The concrete delivered to a skyscraper foundation must have a precisely known 28-day strength, verified by a laboratory test on a sample from the same batch. This is non-negotiable. It is the bedrock of quality control, of legal liability, and of the complex financial models that underpin every major project. Investors and insurers need guarantees, not the nuanced judgment of a master tasting volcanic dust. This creates a seemingly irreconcilable tension. On one side, we have the ancient model, a hyper-localized, artisanal approach that yielded legendary durability, but was inherently unpredictable and impossible to scale globally. On the other, we have the modern model, a globally standardized, scientifically controlled system that enables our vast, interconnected world, but often prioritizes short-term predictability over long-term resilience. The challenge for our future is not to choose one over the other, but to find a synthesis. The path forward may lie in a new kind of material intelligence. Imagine a construction site where sensors in the mixing truck analyze the humidity and temperature of the day, the specific mineralogy of the local sand, and the chemical composition of the industrial pozzolan being used. This data feeds into an algorithm that has learned from thousands of ancient and modern mixed designs, and it dynamically adjusts the recipe in real time, creating a bespoke concrete optimized for that exact location and purpose. This is the promise of digital fabrication and smart materials, a way to automate the ancient structure's artisanal wisdom. We could move from a paradigm of mass production to one of mass customization in construction, where every pore is uniquely suited to its role, its climate, and its expected lifespan. The goal would be to embed the deep, contextual knowledge of the past into the precise, scalable tools of the present, creating a new language of building that speaks in both codes and conversations. The master builder's artisanal touch has found its echo in the laboratory, where scientists are now designing concrete with a biological sense of self. This new frontier moves beyond simply copying the Roman recipe. Instead, it asks a revolutionary question: what if concrete could sense its own injuries and respond, not over centuries but in weeks or months? The most promising answers are emerging from a field known as biomimicry, the practice of imitating nature's time-tested strategies. Here, the inspiration is not just ancient Rome, but the human body itself. Think of how a small cut on your skin triggers a complex cascade of clotting and cellular repair, a process that happens automatically without conscious thought. Researchers are now engineering concrete to possess a similar, if simpler, autonomic nervous system. One approach involves creating a vascular network within the material. Imagine thousands of tiny, hollow glass fibers or biodegradable polymer tubes running through the concrete like a network of capillaries. These tubes are filled with a liquid healing agent, often a silica-based compound or a special resin. When a crack forms, it fractures some of these capillaries, breaking them open. The healing agent then wicks into the crack by capillary action, much like blood rushing to a wound. Once exposed to air or moisture within the fissure, this agent hardens, forming a solid, glue-like patch that bonds the crack shut from the inside out. It is a targeted, on-demand repair system triggered by the damage itself. Another fascinating technology borrows from materials used in spacesuits and medical devices: shape memory polymers. These are special plastics that can be programmed to remember a specific shape. Researchers embed fibers or particles of this polymer into the concrete mix. Under normal conditions, they remain passive, but if a crack appears, maintenance crews can apply a targeted heat source, like a handheld induction heater, to the affected area. The heat causes the shape memory polymer to contract, pulling the sides of the crack back together, like a suture cinching closed. This physically closes the gap, which can then be sealed more permanently with a secondary agent. It is a powerful tool for managing larger, more visible fractures before they become critical. Yet, the most poetic and perhaps profound innovation takes its cue not from human physiology, but from the humblest of Earth's organisms, bacteria. In this method, specially selected spores of bacteria, often from the genus Bacillus, are mixed into the concrete along with a food source like calcium lactate, encapsulated in tiny, protective clay pellets. These bacteria are extremophiles capable of lying dormant in a state of suspended animation for decades without water or oxygen. They sleep within the stone. The system activates only when failure begins. When a crack forms and water inevitably seeps in, it dissolves the protective clay capsules, awakening the dormant bacteria and releasing their food. The bacteria spring to life, metabolizing the calcium lactate. As a natural byproduct of their metabolic process, they precipitate calcite, pure limestone, effectively excreting tiny crystals of stone. These crystals grow and accumulate, gradually filling the crack completely. After the crack is sealed and the water and food are consumed, the bacteria return to their dormant state. It is a beautifully closed loop, a symbiotic relationship where the living organism heals the non-living structure, and the structure provides the organism a protected home. This is not science fiction. Small-scale pilot projects using this bacterial concrete have already been used to repair historical structures and line irrigation canals, with documented healing of cracks within a matter of weeks. While these are high-tech interventions involving nanotechnology and microbiology, their goal is elegantly simple: to restore the autonomic healing function that Roman concrete possessed inherently. They offer a glimpse into a future where a bridge could sense the formation of a fatigue crack after a long winter and begin secreting its own mineral scar tissue by the following spring. This represents a fundamental shift from viewing concrete as a static, inert material to treating it as a dynamic, responsive system. We are learning to build structures that are not just strong, but are alive with the potential for renewal. Every new construction site is a massive withdrawal from the planet's material bank. The energy required to mine the aggregates, fire the kilns, forge the steel, and transport it all is staggering, a carbon debt paid upfront in the atmosphere. When we design a structure to last only 50 years, we are making a profound statement about value. We are saying that this immense investment of planetary capital is acceptable for a single human lifetime of service. It is a model of planned obsolescence applied to the very skeleton of our civilization. The ancient approach challenges this at its core. A harbor that stands for 2,000 years is not just an engineering marvel, it is a monument to radical resource efficiency. The energy and materials invested in its construction were amortized over not decades, but over hundreds of generations. That single act of building eliminated the need for countless cycles of demolition, disposal, and reconstruction, each with its own fresh toll on the environment. In a world facing climate crisis and dwindling raw materials, this is no longer just a historical curiosity, it is an ethical imperative. The conversation must shift from the initial price tag, the cost per cubic yard of concrete, to the true cost of stewardship, the cost per century of reliable service. What is the real price of a bridge that must be torn down and replaced 3 times in 300 years, compared to one that, with mindful maintenance, stands for the entire span? The latter, even if more expensive to build initially, represents a staggering saving of energy, material, and carbon over time. This is a form of intergenerational responsibility written in stone and mortar. We are the temporary stewards of finite resources. When we choose short-lived materials and designs, we are forcing future generations to repay our carbon debt again and again, while also dealing with the mounting waste of our crumbling infrastructure. Choosing durability is an act of foresight and respect. It says we value the well-being of those who come after us enough to invest more today, so they will not have to spend even more tomorrow. It transforms construction from an extractive industry into a legacy project, where the goal is not merely to build, but to build something that remains worthy, useful, and beautiful for as long as possible. This philosophical shift reframes every crack, every repair, every material specification. It asks us to see our buildings and bridges not as disposable products, but as the enduring gifts of our age to the future. Our journey from Pozzuoli's volcanic ash to the laboratories of MIT reveals a profound truth. The ancients were not merely builders, they were master material scientists who engineered for time itself. Their self-healing concrete was not a single ingredient or a lucky accident. It was a synergistic masterpiece, a perfect alignment of reactive chemistry, intelligent material selection, and a design philosophy that embraced slowness and environmental harmony. Each component, from the volcanic Pozzolana to the porous tough aggregate and the hot quicklime mix, played a role in a slow, perpetual conversation. This conversation turned cracks into sites of regeneration and seawater into a strengthening agent. They built with the understanding that true strength is not a moment of perfection, but a patient, ongoing relationship with the world. We stand today amid the towering achievements of our own age, structures of breathtaking scale and complexity. Yet the silent lesson from those older stones challenges the very foundations of our modern world. It asks us to reconsider our core values, to weigh longevity against speed, adaptation against rigidity, and stewardship over disposal. We cannot and should not simply revert to Roman techniques. Our world requires the steel, the span, and the speed that our materials provide, but we can and must integrate their timeless wisdom. The next chapter in the story of concrete is being written right now in research labs and on pioneering construction sites. It is a chapter that must blend our formidable modern knowledge with the ancient insight that the best materials are those designed to endure, to adapt, and to heal. This is not just about better concrete, it is about a better philosophy of building, one that sees our infrastructure not as a cost to be minimized, but as a legacy to be maximized. If this exploration has changed how you see the world beneath your feet, the bridges you cross, or the cities you inhabit, we would love to hear your thoughts. Share them in the comments below and subscribe to continue deciphering the hidden codes of history with us.